Hello, welcome. In the last video, we discussed the field due to a uniform disk at a point on its axis. In this video, we are going to discuss the field due to a uniform thin spherical shell. So first thing we need to do for doing this is we need to draw a spherical shell, and this is the center of that shell, and at this point we will be considering the field. Let us call this the point P. The distance of point P from the center of this shell is R, and here we consider an area element of thickness a d theta, and if we consider the distance here, this the distance of this point from this point is z, and a is the radius of this spherical shell. And if we take a perpendicular here, the length of this perpendicular would be, if this angle is theta, it would be a sine theta, and we will consider this angle as alpha. Okay, now first we need to consider the density. For that we need to take a consideration that the mass of this spherical shell is m, and we know the area of the spherical shell equals 4 pi a square. So now the density would be and we see that the circumference of this circle will be and this slight width is AD theta. So if we multiply this by AD theta, we will get the area element. That becomes 2 pi a square sine theta d theta. We get the mass element dm by multiplying these two quantities. So it gives us m by 2 sine theta d theta. This is the mass element dm. Now we know for a ring, the electric field at point P becomes now this field gdm by z square will be directed along this direction, but you see that for the element here the field is directed along this direction, but there is this symmetric body, so there is element here also, which in turn will give rise to a field in this direction. So the components that are perpendicular to this axis, they cancel out from here and here, and ultimately the components that are along this line, along this axis, they remain. So we'll be taking the cos components, and this angle is alpha also, you can clearly see from the geometry here. So we'll take only the cos alpha components of the electric fields due to the elements. So we'll multiply here by cos alpha. Now what we need to do is, first thing we'll do is we'll express the z in terms of a and r and the angle between them. H square equal to square minus 2ar cos theta. 2z dz equal to ar sin theta d theta sin theta d theta equal to z dz by ar. This is the result we will use later in the derivation, and another result we need to derive is for this, that is a square equal to z square plus r square minus 2zr cos alpha. So let us write this. Now we need to find cos alpha, so we'll write so from the expression of dE we can write dm is 1 by 2 into cos alpha is so, and if we integrate we get E as integration gm 4 sin theta d theta we know is z dz by dr ar, sorry, one by z cube and here is a r that makes it r square, and here z square plus r square minus a square. So we'll take this ar square outside, integration one plus r square minus a square dz, and this equals now we will need to put the limits, and upon putting the limits we will be finding the fields at different points inside the sphere, that is the spherical shell. So first we will be considering that the point P is outside the shell, that is r greater than a. So if that happens, from the expression of the electric field we can write E equal to gm by 4a r square z minus r square minus a square by z. So the limit will be from r minus a to r plus a. So we'll be putting the limit here, gm by 4 plus a minus, it gives us 2a minus minus 2a, so minus r square minus a square into minus 2a by r square minus a square. So that gives us gm by 4a r square times 4a gives us gm by r square. So this will be the field when the point P is located outside the sphere, and now we'll consider the field for a point that is inside the shell. So for a point inside the shell, the limits will be from a minus r to a plus r. So from the expression we can write E equal to gm by 4ar square z plus square minus r square by z from a minus r to a plus r. We can write gm by a r square 2r plus a square minus r square minus 1 by a minus r. That gives us gm by 4ar square 2r plus a square minus r square into minus 2r by a square minus r square. So if these two terms cancel out, it becomes gm by 4ar square 2r minus 2r. This becomes 0. So we can see that the field due to a spherical shell is equal to gm by r square for the point P is located outside the spherical shell, that is r greater than a, and if the point P is located inside the spherical shell, we can write E equal to 0. So this is the result of our derivation. I hope you like this video and see you in the next one.